So let's look at an application problem. Number 12 from the exercises in the textbook says if a rock is thrown upward on the planet Mars with a velocity of 10 meters per second, its height in meters after t seconds is given by capital H equals 10t minus 1.86 t squared. I have 4 parts here, and part A asks us to find the velocity of the rock after 1 second. So, we know how to find velocities based on what we've talked about in the textbook. That is the same as the slope problem, and it can be computed from the derivative, the limit of the difference quotient. The specific value at which we're evaluating in this case is a equals 1 second. Now, some examples in the textbook show how sometimes we will evaluate the derivative at a general value a, and then plug in different particular numbers so that we can avoid having to repeat the limit. And looking ahead, we can see that that is what we will be doing here. But I will stick to the spirit of the question and pretend I don't know what else we'll be doing, and only look at the 1 second case. All right, so we want the velocity v will be the limit as h approaches 0 of f of a plus h minus f of a all divided by h as our standard difference quotient there. And in this particular case, a is equal to 1. So if I write that, we have f of 1 plus h minus f of 1 all divided by h. So now plugging that into the function we're given, it wasn't given a function name, it's just the variable capital H. Note that capital H and lowercase h are unrelated variables. Make sure to keep those straight. So we'll have the limit as h approaches 0, f of 1 plus h, so we're just putting 1 plus h in for our variable. In this case, that's t. So we have 10 times t, so that's 10 times 1 plus h, minus 1.86 t, that's 1 plus h, squared. So there's our first function, minus f of 1. Well, plugging in 1, we have 10 times 1 minus 1.86 times 1 squared. This is why I tend to use these square brackets here, because you're subtracting one function from another, and if there's more than one term in the function, you need to make sure that you have grouping symbols so that you don't make a sign error. But this is all over h. Now we need to start expanding and simplifying and see what we get. So we have 10, let's distribute that. So we have 10 plus 10h minus 1.86 times, when we square 1 plus h, we get 1 plus 2h plus h squared. So there's our first function. Minus, the second function evaluation is 10 minus 1.86. That's all over h, but that's getting cumbersome to write, so I'll do a trick like I did last time. I'll put that into grouping symbols and say that it is multiplied by the reciprocal of h. Pardon me. Continue simplifying. So we have 10 plus 10h minus 1.86 minus 3.672, I guess, h. We'll find out later if that is correct. Minus 1.86h squared minus 10 plus 1.86, close parentheses, times h inverse. Okay, so let's simplify what we can. Frequently, especially when we're dealing with polynomials, terms will cancel. So you see we have a 10 minus 10. We have minus 1.86 plus 1.86, so that's nice. Look to see if anything else cancels. It doesn't look like it. We have 10h minus 3.72h, so that is going to leave 6.28h, if I'm doing my mental arithmetic correctly, minus 1.86h squared times h to the negative first. That is the limit as h approaches 0 of, pushing this through, we see that each term now has an h in it. So when we multiply the h inverse through, we get 6.28 minus 1.86h. And now we can do some direct substitution, putting in h equals 0. 0 is at that term, and we are left with 6.28. Okay. So let's come back up to what part A said. We got 6.28. And what is this? It says find the velocity of the rock after 1 second. So this is supposed to be a velocity. And looking at the way this, the units are used in this problem, we expect that to then be meters per second. As an aside, remember that one way of thinking about these, one of the notations that was given was the limit as delta x approaches 0 of delta y over delta x, right? We're looking at an instantaneous rate of change. So if you look at what we're doing here with this difference quotient, we're looking at a difference of function values, and the function values are supposed to be a height. That is a height in meters, right? So the change in height, let's say here we have delta h over delta t is what we have going on, right? The change in height is measured in meters. Time is measured in seconds, so the change in time is measured in seconds, and we have meters per second. And those are precisely the same units that we have here. So if you're doing an application problem that involves derivatives and rates of change and stuff like that, and you're having difficulty interpreting things, maybe you're not sure what units you should use, or maybe you're not sure what the derivative means, or even if the derivative is appropriate, you can take the units for these quantities and divide them and see what you get. Meters per second, that is a distance per time, that's a speed, that's a velocity, right? So that sounds good. Awesome. Now, part B, they ask us to find the velocity of the rock when t equals a. So this will be mostly the same, except more general. So for part B, we want to do all of this at a. So again, we have the limit as h approaches 0 of f of a plus h minus f of a, all divided by h. But the difference here is that we are not substituting in a specific value for a. We're just plugging that directly into our function. So we have 10 times, where was that? Here we go. It's no longer on my screen, so I have to check my notes. A plus h minus 1.86 times a plus h, quantity squared. That is f of a plus h, minus the function evaluated just at a. So this is much simpler. We are simply plugging in a where our variable is. So we have 10a minus 1.86 a squared. And this is all over h. I probably should have moved that to the end, but whatever, I'll do that in the next step. So, distributing and simplifying a bit, we have 10a plus 10h minus, let's correct that string mark there. Let's see here, we'll have an a squared, so I'll have a 1.86 a squared. Squaring this, we have a 2ah, so we have minus twice that, that is 3 point, what did I say that was, 72, I think. AH. And there will be a plus h squared, so we have minus 1.86h squared. Minus 10a. Minus 1.86a squared. And I guess I lied. I'm not actually going to do this times the h just yet. Let's actually take those brackets out. They don't help us. I've changed my mind. Can't quite fit that. So that means I just have to do all of this junk. All of that divided by h. Hopefully your paper is wide enough to hold your handwriting. My screen is a little more limited. Let's see what cancels. We have 10a minus 10a. We have, I made a sign error. We have minus negative 1.6a squared, so that becomes a plus 1.86a squared. That is important because that needs to cancel. One of the reasons to kind of pay attention to how patterns in these problems go, do a lot of problems, pay attention to what happens, look at the kind of structures that happen, you start to get an idea of what to expect. And it's important to not make assumptions, right? You don't want to just say, oh, this is going to go like this, I don't have to worry about it, because sometimes weird stuff happens. But if something happens contrary to your expectation, then that can give you a clue that maybe you should look at it a little bit closer and see what's going on there. But yes, in this case, we have canceled some terms. We have 10h minus 3.72ah minus 1.86h squared, all divided by h. You'll note that all the terms that did not have an h in them canceled, so now we can actually do that division by h, so that we end up with 10 minus 3.72a minus 1.86h. And when we take the limit of that as h goes to 0, limit of 10 is 10, limit of the negative 3.72a is still itself. The variable a is treated as constant with respect to the limit, because we're only looking at what happens as h goes to 0. But plugging in 0 for h zeroes out that last term, so it looks like we have 10 minus 3.72a. So if we come back up here to part b, we have 10 minus 3.72a meters per second as the velocity of the rock when t equals any value a. Okay. Now, as a quick check, this is supposed to work for any value a, so it should also work for a equals 1 second. If we plug in 1 here, we can confirm we have 10 minus 3.72, leaving us the 6.28. We confirm that we get the same result as we got in part A. So we did similar things, but our answer to part B is more general. It answers A, but also later questions as well. Like I said, if you know that you're going to be finding this value at more than one place, you probably want to do it in general, so you only have to evaluate the limit once and not have to grind through all of that again. But I just wanted to illustrate how this would go, keeping in the spirit of the problem. Part C asks us, when will the rock hit the surface? Do I have enough time to do that? Or not time, but space. I guess I could, but let's just go ahead and pop over to some extra workspace here. We have, what was that? H equals 10t minus 1.86t squared, right? Yes. And for part C, we're asked, when will the rock hit the surface? And h is the height, so we can assume that that happens when h equals 0. So we have the equation 0 equals 10t minus 1.86t squared. So 0 equals t times 10 minus 1.86t. This has two solutions. One is when t equals 0, or the other is when 10 minus 1.86t is equal to 0. So if we add the 1.86t to both sides and then divide, we get t is equal to 10 divided by 1.86 seconds. Okay. Now the time t equals 0 is when we start. This is when the rock is thrown. so we can assume that it is thrown from approximately ground level. And then it comes back to that level after this many seconds. And let's see, if my notes are correct, that is approximately 5.38 seconds. I don't know how accurate we want to make this because we don't necessarily know how precise the initial velocity was. Again, we don't really do much with significant figures in this. This is a pure math class. You'll generally be told how to round things if the rounding matters. But that's pretty much what we're looking for there. And then part D asked us, with what velocity will the rock hit the surface? Well, we know when the rock hits the surface at 10 over 1.86 seconds. And we know how to find the velocity at any particular time A. That is this value we found in part B, right? We have 10 minus 3.72a. A here is 10 divided by 1.86 seconds. So the velocity is 10 minus 3.27. I'm copying that right. 72. I got that backwards. Let me fix that. I knew that didn't feel right. Too many things to keep track of at once. 72. Is that right? Yes, there we go. Times A, which is 10 over 1.86. So we have 10 minus, now if we remember this 3.72 was 2 times 1.86, that's where that came from. So we have 10 minus 20, which is negative 10 meters per second. This makes sense. This is a very simple model, so we can assume that we are neglecting things like air resistance. The rock would follow, if we plot this as height versus time, if we have height versus time, we expect the rock to follow a parabolic trajectory, which should be symmetric. So if its initial velocity is 10 meters per second, its final velocity when it comes back to the same level should be negative 10 meters per second. Note that this says velocity and not speed. If you have studied physics or done anything with vectors in the past, you are aware that velocity includes not only a magnitude but also a direction. The speed is 10 meters per second at either end, but we have an orientation here where up is positive. So the original velocity of 10 meters per second was positive, meaning that it is an upward velocity. Here we compute a negative velocity. That means that the object is moving downward. So that distinction between positive and negative will be important. And it's nice that the math just takes care of itself. The math we use for derivatives, that's also related to slopes of tangent lines and things like that, will tell us whether something is increasing or decreasing based on whether it's positive or negative. It just comes out in the computations. So yeah, hopefully that makes some sense. Again, sometimes thinking about the units and interpretations of those can help with understanding what things mean in these contexts.